reverse me. It didn't just print out the string again, it printed out two slices. So if I were to make this just the first word, like so, and I ran this again, it would just say the word reverse. So how does this work internally? Well, internally, we don't actually store this new word called reverse or me. Internally, data structure stores the starting position and the length of the slice, which is the ending index to the starting index. So that's just a simple like math sum there. Ending index minus starting index is the length of the string. So for example, the word2 variable contains a pointer to the 9th byte in reverse me and has a length of 10 minus 8, which is 2. So let's see how this actually looks like. So this is our actual string here, reverse me. And this is the full thing. This is the whole collection. For word2, firstly, pointers are variables that point to a section of memory. You learn more about this in 225 and 241, but all you have to know is that this points to a part of memory. So the pointer for word1 starts at here. We start at the 0th index, so our pointer starts here. We know that the length is 9, so we go from the 0th index all the way 9 characters along till we hit here, and we get the word reverse. And for our second example here, we start at the 8th index, because as we remember from our code, we start at the 8th index, and has a length 2, because 10 minus 8 is 2. So we have 2 characters, starting from the 8th index for our second word. The good thing about this is that instead of taking extra space to store this word again, we can simply store these references, and we save space when we're trying to make a large slice of something. So using this dot notation, we can do a few very clever things. And this is something you've also seen in Python. So let's say we want to slice a string s. So we want to go from 0 to some index. We can just write no 0 there, just going to some index. So we write blank dot dot some index. Similar to Python if you want to go from 0 to some index. Vice versa, if you want to go from some index to the end of the string, we can just write some index dot dot. In Python, you write some index and then a colon. Finally, if you want the whole string, we can just write s dot dot, and that'll give us the whole string, again, similar to Python. So final bits, the string slice type is written as ampersand string, and that's because this is a reference to the string. So this is, for example, if you want to explicitly label a variable type, or if you want to have a return from a function or a parameter. String literals are string slices, so if you make a literal, that is equivalent to a string slice. A literal being instead of like using the keyword from like we did here, which creates this array, you use a literal like so, that's a slice. It's not an array of characters or vector of characters. So here's some other slices. So we can use slices on other collections like arrays. So let's say we have this array with the words 196, 196. If we take a reference sum array and slice it from 1 to 3, we'll start here at the first element and go up to the third element but not including it. So we'll just get 9 and 6, like so. And again, this is very similar to Python. You've seen this before, so it shouldn't be too surprising. Let me take a quick look if there's any questions in the chat. All right, no questions. So now let's look at structs. So structs are a custom data type that allow you to group a set of values that make a meaningful group. So for example, if we wanted a student struct, we would store things like their name, their UIN, are they a 196 student, and their GPA. So these are all different values, but they're all related to the same person, so they're meaningful and they should be grouped together. So how do we create a struct in Rust? So here is like a really dummy template. So we declare a struct by using the keyword struct followed by the struct name. So the keyword struct, whatever the struct name is, and now here's the important part. In the struct, we define a comma-separated list of key value pairs. So what that means is, for each value here, we have a key, and then whatever that value is. So for example, in our UIUC student struct, our key could be name, and the value could be that person's name. So let's take a look at our example struct here. So our struct here is for a UIUC student, so we use the keyword struct, call it UIUC student, and we have, notice this comma-separated list of key value pairs. The key being whatever we're trying to label, so the name, and then the value here for when we're defining our struct is simply just the type. So our name is a string, our UIN is an unsigned 64, if their 196 is a boolean, and the GPA is a float. So let's actually use this in our own program. So let's declare a struct using code. So to do that, we use the let keyword, and then within the brackets, we assign the key value pairs. So notice here, we use the let keyword, name our variable, and then we define a UIC student struct. Important point here is the order of the key value pairs don't have to match the struct declaration. So if I wanted to put N96 first, the GPA, and then whatever, it wouldn't matter because we're actually explicitly defining the key. So this is our student. Their name is Ewan Knightley Sticks, 196. I thought it was really funny. Their UIN is this. They're in 196, and the GPA is a 4.0. So how can we use this now? We have the struct that's storing all these values. That's really cool, but we can't do anything with it yet. So we can access the values in the struct using dot notation. And that's pretty basic. You've probably seen this in Java or C++. You just take the struct, use a dot followed by whichever value you want. So if we were to run this code, it would say the student is called Ewan Knightley Sticks, and we can run that here. We simply get that person's name. We could also say the student has GPA, and we can just change this to their GPA instead. And we get a GPA, the 4.0 GPA. They're a smart kid. Oh, sorry. But we can also access the values using dot notation. So let's say our student suddenly joins and they didn't do too well their first semester. They didn't take 196, so obviously they're not as smart, and the GPA kind of dropped a bit. How would we want to edit their GPA? So we can also, again, use dot notation. So we'd go here, have our student here, take their GPA, and change it to whatever we wanted it to be. An important thing to note here is that we can only change the values of mutable structs, and the entire struct has to be mutable. We can't simply make their GPA mutable and their name immutable. Even though that would make sense, Rust doesn't let us do that. So since our entire struct is mutable, we can change the values here. So obviously when we print this out, we're going to get mutable student, because that's their name, their new GPA is 3.3. So even though we initially assigned it 3.5, it changed to 3.3, like so. Again, it has to be mutable for us to be able to edit the values of this struct. Yep, as we mentioned here. Now let's say, how can we use a function to create a struct? So if we create a function like this, so we know we use the fn keyword, function name, and we pass in our two parameters, and we're returning a UIC student type. Let's break this down. So the type is the function for our struct name. We're only passing two parameters here because if we have a new student, for example, they obviously aren't registered for any classes, so we hard code what their 196 status is and their GPA, because the moment you come in, you have 4.0 GPA by default. So we only actually need their name and their UIN. So we're hard coding these two and we're passing these two in. Yeah, let's do a quick demo here. So notice that for this to work, I couldn't keep the struct in the main, because if I keep the struct in the main, it'll set the scope of struct to only the main. So other functions, like this one here, wouldn't be able to use it. Now that it's global here, any function within our Rust program can use this struct. So we're going to create this student called function student, and their name is function student, and this is their UIN. So obviously it goes into our function here. We assign the name, we assign their UIN, and we set their GPA to 4 and their 196 status to false. Notice that there's no semicolon at the end of this, so we don't have to explicitly return. This will automatically return this UIC student and assign it to func student. So when I run this, our function student's name is function student, so function student's name, or GPA, sorry, is 4.0, or 4. Any questions about that? So someone asked, so all the variables can be all mutable or all immutable? So yeah, if you're talking about the struct here, within our struct, all the variables or all the values within our struct can either be mutable or immutable. You can't have a mix of that. If we define a variable a mutable variable and assign it to a struct, we can change the values. If it's not mutable, we can't change the values once it's been assigned. Okay, but doesn't this seem sort of redundant? I'm sure as a programmer, if you were to write a really big struct, like let's say we had a student and all their information, like their hometown, their phone number, it's kind of redundant to have to manually assign like their name, their UIN. Like think about it. The struct's name variable, so name, is being assigned to the value in the parameter called name. Similarly, the struct's UIN variable is being assigned to the value in the parameter called UIN. Like this isn't that impressive. It's very, very obvious. And it seems pretty obvious to us too, and it's obvious to Rust as well. So what we can do instead is use the field init shorthand when struct variables and parameters have the same name. Init here is short for initialize or initialization. So we have this new student here. And notice instead of assigning all of the parameters by hand, we can just say name UIN. There's no equal sign here. Since the variable name and the parameter names are the same, we don't need to manually assign them. Rust will just assume, Rust knows that they're true and will assign them automatically. Obviously, it's not that useful in a very small struct like this, but if you have a really massive struct, then it's much more useful. And again, the code is here if you want to run that yourself. I'm not going to do it because it's very, very similar. So sometimes we want to make a struct that uses most of the values in an older struct with a few updates. So we will use struct update syntax to do this. So let's say we have this struct here. So this is our student one. These are all their pieces of information. What we could do is we could reinitialize all these student 2 with similar values. So we can call this person student 2, give them their UIN, but then copy over student 1's GPA and student 1's in 196 status. But this is unnecessary code, and again, Rust helps us be lazy and speed up this process. So a better way to do this is using the struct update syntax. So what we do is we firstly manually assign the values we want to change. So student 2 obviously has a different name and a different UIN. Those are unique to the student, so we want to manually assign that. But afterwards, we use the ... to indicate that any field not explicitly specified should have the same fields as the given instance. So in this case, the given instance is student 1. So what this will do for us, when we run this, it'll copy over student 1's GPA and their in 196 status, because that's what's not been explicitly specified before. And if we print this out, we get student 2's GPA is 4, because that's what student 1's GPA is. Does that make sense to everybody? Any questions about that? All right, no questions yet. We can also make something called tuple structs. So tuple structs are basically structs that look like tuples. It might seem a little redundant to have it this way, but it helps us when we're having very large programs to know exactly what this type of struct is meant to be doing. So they're similar to structs in the way they provide meaning by their name. So tuple structs for coordinates can be called coordinates, for example. Instead of using a regular old tuple, we can explicitly say this is a coordinate. The main difference is the fields don't have names, only a type. Again, this is useful when you want to give a tuple structure a name and give it meaning in your program, instead of just using an arbitrary tuple that could be confusing for other programmers. Let's take a look at this example here. So this is our tuple structs main function. We define our struct here using the keyword struct, give it a name, and then we use the tuple syntax. We use the round brackets there. And instead of explicitly giving a name, like a key value, we just specify the type. So we know the test scores is an I32 with 3 I32 values, and lecture reviews are also just 3 I32 values. And this is how we would assign this to a variable. So again, notice we only define the types of the struct holds, we do not name the values, and we use round brackets because it's a regular tuple. Something important to note though is that even though these two have the exact same type, these are different, the exact same structure and types within their tuple structures, they are different types. So if function parameter is test scores, you could not pass lecture reviews into it because they're different types. We explicitly said that. So even though they look the same, they are different because we named them to be different. And this just helps when you're writing like code that needs to have meaning. Having specified struct tuples will give meaning to your code and make sure that things don't get wonky and like we don't use variables that shouldn't be used in certain functions, for example. I did want to go over this example to show you how you can use this. Again, because this doesn't have a name, it's only a value, we can access the different indexes using the dot notation. So we use .1 to access the first value, or sorry, the second value because we're 0 indexed. .0 would get the first value, etc. So if we run this, we know the second test score is test scores.1, which is 20, which we see here. The final lecture review is lectures.2, which is 5. Essentially, they're basically just tuples, but we give them meaning by giving them a name. So any questions, guys, about any of the struct stuff we cover, any of the slices stuff? Put them in the chat right now. Nope. Okay. If that's the case, then we're going to go right into the Kahoot. Here's the code. And I'll paste this into the Discord too. I can turn on the Kahoot music too. I'm going to start in about 30 seconds, just so we can make the most of our time. Alright, I'm gonna start the Kahoot. If you're running late, you can just join it whenever you can. Well, it's gonna do a bit of recap of the previous lectures because this is gonna be our final Rust syntax lecture. So scalar data types can only hold a single value. Hooray, good job. So, yep, this is true. Scalar data types can only hold a single value. So that's like our I32, U32 characters. Those are all scalar data types. A bit of recap of our first lecture. So arrays can hold values with multiple data types. True or false? Alright, so this is a bit of a mix. The question was, arrays can hold values with multiple data types. Unfortunately, in Rust, you can't do that. Your arrays must all have the same type. So this was false. Another true or false, the heap is used to store data of an unknown size or size that might change. True or false? This is lecture 2 stuff. Alright, good job. So, yeah, the heap is used to store data of an unknown size or size that might change. You guys pretty much all nailed this question. Apart from you two. Okay. So true or false, a value can have multiple owners. Yep, false. A value cannot have multiple owners. That's a big part about Rust ownership. It's very safe when we have single owners for each of our values. It's also why we don't need a garbage collector. So it makes Rust very fast. Next question. Rust is a single paradigm programming language. True or false? This one might be too tricky, because we kind of skimmed over this. Alright, so false. Rust can actually do many different programming paradigms. So what we're typically going to use is object-oriented programming, which is what you're going to be using in 125. But you can also use like a functional style, many different styles that you can use within Rust. It's very powerful like that. So what keyword do you use to define a struct? So it should be relatively straightforward. Yep, great job. Again, almost all you got it correct. We use the struct keyword to define a struct. I do want to emphasize that because that's really important. When you create a new struct, jumping back a lot, use the struct keyword followed by whatever our struct name is. Very important. True or false, slices are references. True. So slices are references to a certain an existing collection. A string literal is also a reference. I'll quickly speed through the rest of these. How do we access a specific value in a struct? What notation do we use? Alright, cool. So a little bit of a mix here. Most of you got it correct. We use the dot notation and no brackets or anything. So if we wanted to get, for our UIUC student struct, if we wanted to get their name, we would just do like var dot name, like that. Last two, then we'll go back to the cool stuff with today's lecture. So can we make specific values in the struct mutable while keeping the rest immutable? There's a big slide on this, so I hope everyone gets it correct. Oh, is my camera covering part of the answers? Let me change that right now. Thank you for letting me know. Alright, yep. Most of you got it correct again. When we make a struct, we either define the whole struct to be immutable or the whole struct to be immutable. We can't have certain values be mutable or immutable within the struct itself. Even though that'd be really useful, it's safer to have the whole thing be mutable or immutable. Good job. What will this string slice be? So from the third index to the blank index. Okay, I think everyone got it. Alright, yep, so the answer is D, E, F, G. So if we're using what we learned about how this is stored in memory, an easy way of figuring this out is you simply just find the first index, so you go 0, 1, 2, 3, and then we just get, including this one, the next 4 characters, because 7 minus 3 is 4. So 0, 1, 2, 3, and just go from D to G, because those are the next 4 in total. So yep, good job, guys. Last one. True or false, string slices internally hold a pointer length but not capacity. So we have that on the diagram, if you remember. Alright, good job. So true. When we have a string slice, we don't hold the capacity, it's just the pointer and the length. And this is really useful because instead of taking the copy of the entire collection that we were using, we can just get these references to it, and it's really useful. Alright, we can skip this. But good job, top 3, you guys did great. And remembering everything the past couple lectures, so congrats, you guys. Now let's move on to, I think, the cooler part of this lecture. And definitely the parts that you're using a lot. So, actually let me check for any questions. So first thing someone asked, what's a struct? I'd say take a quick skim through the slides. Essentially, what a struct is it's a single data structure that can hold multiple values. So if we have a meaningful group of values, for example, UIUC student, we can hold like their name, their GPA, their hometown, all those important information about them within one value. By using struct update syntax, will the struct have the same keys and values as the original, or does it update the values based on the parameters? So when we use struct update syntax, what we're going to do is we're going to retain the original values that we had. So whatever we explicitly label, like name and UIN, that'll be labeled from whatever we hard-coded it to be. And everything else that we didn't explicitly label will be taken from student 1. The key values in both these variables will be the same. Sorry, the keys will be the same because they're both UIUC students, right? So they'll both have the same set of keys. All right, moving on to match. So match is a really powerful tool that you use a lot when you're writing Rust code. So essentially what it lets us do is use pattern matching by using the match keyword. And this works similarly to switch statements, which you may have seen in Java or C++. But first, let's go over what a switch statement is, because it's not something we use a lot, or I personally have not used. I don't use switch statements a lot unless I'm writing in Rust or Haskell or something like that. So here's a Java switch statement boilerplate. You can think of it like an alternative if-else. So let's say we have an expression, and we'll call this expression x. Or we'll give an output for this expression. So let's say if x is greater than y, or 5 is greater than 3. If the first case is true, then we run this code block, and then we break. If the second case is true, we run the code block and break. If none of those cases match, then we run something else. It makes more sense when we have an actual example. So let's say the day is 4. We want to switch on day. If day is 1, we print out Monday. If it's 2, we print out Tuesday. 3, Wednesday. 4, Thursday. It is 4. So we'll print out Thursday and break out of the switch statement and then print Thursday. Let's say, for example, day was like 100. We'll reach the end, and if there was a default case here, we'd hit the default case and print that out instead. So we can do this in a very similar way in Rust. So this code snippet here that we'll go through, but first let me break this down. So we have this number here, and we're going to try different numbers here. So first things first, we specify our case by putting something before this arrow symbol. Anything after this arrow symbol is the code we're going to run. Anything before it is part of the case. So there's 3 different examples here, or 4 different examples here. Firstly, it's the single case. So let's say if the number is just matching this number here, or if the variable matches this number or this value, we'll run this code here. So if we just want to match something directly, we can do it like this. There's no equals equals required. If we wanted to match several distinct values, then we use the vertical bar to indicate that we're matching several values. So if it's 2 or 3 or 5 or 7, it'll match this. If we wanted to match an inclusive range, then we'll use the range syntax. It's a little weird, notice, because we have this equals there, but if we are anywhere between 13 to 19, and you might remember this from when we're using for loops or just trying to get a slice of something, 13 to 19 is going to be a teen. Finally, we have the default case, and this is actually common in a lot of languages. When you don't care about what the variable name is or what it's going to be, you just put an underscore, and the programming language will say, okay, if it's none of these things, but it's just something, then we're going to print something about it. This is sort of like the else case and if-else statement. So this is if, else, if, else. This is the else case, and if none of the previous cases match, then it'll hit this one. So I want to break this down. Let's pass 11 into our switch statement. So let's make it a little bigger first. So if we pass 11 here, we know that it's not 1, so we're not going to go there. But it does match here, over here. So it's going to print this is a prime. So it's only about 11, this is a prime. Similarly, if we put 19 and ran that, we know it doesn't match the first 2 cases, but because it's in this inclusive range, when we run it, it'll say it's a teen. Finally, if we put 196, actually not 196, let's put a random number, like 100. 100 doesn't match any of our earlier cases, so it hit this underscore else case, and we just print ain't special. This is the very basic information you know to use matches, but this actually gets very, very powerful when we're using optional data types, things like that, which we're going to cover in a sec. So first let's talk about destructuring. So given a struct or a different type of data structure, we can use a match to destructure these different collections. So again, take a look at this chunk of code here. We're passing in a triple. So a triple is simply a tuple with 3 values. So that's it. That's what we're using here. And I'm going to break down these different cases. So this first case here, notice we have 0, yz. What this is indicating is that we only care about what the first value is. If the first value is 0, and y and z are just some arbitrary numbers, we don't care what they are, we can destructure this tuple to get all these values, and we'll match this case. So, for example, here, there's 0 here. 0 is the first value here, it's the first value here. Y is arbitrary, so it doesn't matter what that is. Z is arbitrary, doesn't matter what that is. But because they match, we can hit this case, and we can print out what 0 is, because we know that by hard coding it, and we can get y and z because we destructured this. Instead of passing this entire triple, we get the individual values inside it, and we can print y and z. I just wanted to really emphasize that we're not passing into this function here, or this line of code here, we're not passing this whole triple. We're passing the individual values, or sorry, we're only passing y and z. It's not the whole triple, just the value for y and z, which is why we can print it like this. In our second case, we have something different. It's very similar to the first case in that we only care about the first value, but we can't use the second 2 values. Because we didn't explicitly define that in the match case, this chunk of code doesn't know what those values are. If we tried to print x or y, it would crash because we didn't explicitly specify x and y. So in this example, we're just getting the first value, we want to match that to 1, and whatever the rest of the tuple is, we don't care. That's why we put a dot dot. Finally, we have the else case, which is an underscore. And this I do want to run through because I think it's really important to understand how destructuring works. So let's run this first example. So we know that 0 matches here, and y and z get passed into our function, or not our function, our line of code. Y and z get passed here, and when we run this, we print first the 0, y is whatever the y value is, and then z is whatever the z value is, which is what we're seeing here. We couldn't do this in the second case, because we aren't explicitly defining this, we aren't destructuring it, we're just saying we don't care what everything else is. So we just say first is 1 and the rest doesn't matter. Finally, if we did the otherwise case, or else case, if we run this, we're just going to say it doesn't matter what they are, because none of the previous cases match. That's our else case. Destructuring isn't restricted to just tuples, however. We can also use destructuring when we're using structs, when we're using references, other data structures. So it's a really powerful way of breaking down a large data structure and using only the important things that we need. Now I want to talk about guards. So you might notice that previously these cases are kind of simple. Like they're obviously hard-coded, like it's only if this matches this explicitly. But what if we wanted a larger condition, like an equation or several like if statements? We can use guards instead. So guards are used to have more complex cases using if conditions. It's a little different from an if statement because instead of explicitly starting with f whatever, we say x if x matches this. So we're passing x into this if x matches that. So here's fizzbuzz, or sort of like a watered down version of fizzbuzz because we aren't going from 0 to n. But once we pass a number here, if x mod 5 and x mod 3 is 0, we print fizzbuzz. If it's only mod 3, if it's only divisible by 3, then we print fizz. If it's only divisible by 5, we print buzz. Otherwise, we print the number. And actually, that should say, yeah. So we print the number here. So obviously, the code snippet didn't update there, so can't run that unfortunately, but I will update that later for you guys so you can work on that. But does this make sense to everyone, how the guard works? The guard essentially lets us have a more complex condition before trying to do a match there. Any questions, guys? I see someone is typing. I want to be very clear before we go to vectors because we're going to be using matches and vectors a little bit. Okay, I'm going to move on to vectors. Oh, someone said, at what point wouldn't you just use if-else statements? So the reason this is really powerful is because of the destruction capability. The reason you want to use match instead is because if you're using this sort of notation, you can handle things like, let's say you're trying to dereference a pointer. If that pointer doesn't point to anything, you have to explicitly check for that within your if statement. But here you can just use two matches and say, does it point to something or does it not point to something? Which I'm going to actually cover in vectors. So let's go right into there. It'll make sense. So vectors are data type that everyone knows and loves. It's essentially an array, but it's resizable. Vectors are a powerful collection because they let you hold more than one value in a single data structure, and it's also scalable. And these values will be placed next to each other in memory. We refer to our vector using notation vect, where t is a specific type. And like arrays, vectors only store values of the same type. So here's how we create a vector. We create a vector by calling vec_new, this keyword here. Notice here that we actually specified the type of our vector. We don't normally have to do this, but because this is an empty list and Rust doesn't know the type of our vector, we specified it here. So it's a vec, which holds signed integers of 32 bits. But often when we're writing our code, when you create a vector, we will have initial values inside it. And Rust can just infer what the type of our vector is from there. So if we're initializing it with values already, we can use the Rust macro for convenience. This Rust macro vec exclamation mark, because the exclamation mark explicitly says it's a macro. So we say let v equal this vector, 196. And it'll probably, by default, use i32, because it can infer from the values here that this is an i32. So now updating, this is obviously the really useful part about this. We can add elements to our vector using the push method. And again, our vector has to be mutable to be able to edit it like this. So we say let our mutable vector equal 196. We can push these values to the end of our vector. Someone asked, will we get into macros sometime during the semester? Unsure. I don't think we'll probably go into macros. Macros are just built-in Rust commands that make doing things easier, like println, for example, is a macro. I'm not sure if we'll go further into that just because it's not super related to what we're covering later on. So finally, or not finally, I want to go over read. And read is where we're going to see match. So we can read over a vector like so. So let's say we have this vector again. We're going to call it 196. In our first example here, we're reading it in a way you probably remember from strings. We're taking a reference of vector, and we're going to get the second element. Or second element. What this returns is a reference to the second value in the array. And this is similar to string slicing. We aren't getting the value itself, we're passing a reference to it. So you can probably guess what this is going to do. Now what gets interesting is if we use the get command. So if we use v.get, what that returns for us is it'll return an option type, which we can destructure using match. So if we use v.get, we get an option type for whatever is at the third index. So option represents an optional value. So an optional value can be either two things. It can be a sum type, which contains a value, or a none type, and it does not contain a value. You can think of it like how, sort of in a polymorphic way, where option is like the main class, and you have two subclasses within option, which is your sum type and your none type. So if our array returns something, we get a sum type that has a value. If it doesn't return anything for that, we get a none type. So if we do match v.get2, we'll get an option type, and if this option type is sum, we say sum, whatever the value is, we're going to call it third. We want to take that and print it here. So if it's a sum type, we take its value by destructuring it, and we just print out the third element is blank. If we get a none type, we just print there's no third element. Similarly here, if we look for the 100th element, if it's there, we destructure the sum type because the sum has the value, and then we print out the 100th element. That should probably say 100th, not third. But if it doesn't, we'll say none, there's no 100th element. So since we have a third value in our array, we will get a sum option with a value, and we give the value part the name third, and print this out later. But since we don't have a 100th value, we get a none option type, and this matches our second case, so we print out our error message instead. So this is obviously really powerful because it ensures that we don't have errors like index out of bounds when reading vectors in Rust. I'm just going to download this real quick. So as expected, our second value is 9, our third value is 6, and there's no 100th element. So using the get method is a really powerful way to use match to ensure that we write safe code. Let's say we have an incrementing counter instead of like a hard-coded value here, or let's say our array is changing in size. If we use this method, we might end up referencing something that doesn't exist, and our code will panic and crash. But if we use match, we can use this notation to handle our errors and then write more robust code, which is obviously the goal of like good software development. So match is a much better option than simply doing this. Obviously this is easier, so if you know exactly what's going to be there, use this method, but I would advise using match for more dynamic programs. Finally, I want to go over iterating over vectors. So we can iterate over a vector using a C-style loop, so you remember for I in range, and then we can use the read techniques we learned here. We can just do match for the ith element or get a reference to the ith element. But again, Rust is smart. It's a modern language, so we also have a for each option. So this is similar to Python. If we have our vector here, we can do for some variable name, I call it val, in a reference to v, we print whatever the value is. So obviously this is just going to print 196. And we can run this just to be totally sure that it works. 196. We can also do a regular for I in range loop and then just read it using this method of reading it like so. So either method is viable. If you have to use a different sort of iterating pattern, like iterate every 2 or every odd number or something like that, a for I in range loop might be better. So that's everything I wanted to cover today. Any questions, guys? That was a lot of stuff. So if you have any questions, drop them in the chat and I will answer them to the best of my ability. Also, quick reminder that our social is today, so if you're free,